Carrying on with organic, last video I got this far, I was explaining to you about alkenes and how I really want you to learn organic chemistry using these kind of mind maps. And it's no secret that organic chemistry lends itself to these kind of mind maps because of functional groups. You can fit the chemistry of one functional group onto one sheet of paper and your mind will learn it better. When we were learning these things at university, all of us did mind maps, and we all did them ourselves because it's very individual to you. Now, last lesson, I was talking about polymerization. Polymerization. Let me stick it on a slide thing. So, I was talking about this polymerization here and reactions of alkenes. I was talking about them being addition reactions, like this one. The bromine colour, the orange colour of bromine in bromine water, when that reaction happens, the bromine water loses its colour. And it's an addition reaction where the bromine adds to the carbon double bond carbon bond. Now, carrying on with that, there's some words I need to introduce to you, like saturated and unsaturated, and then for the rest of this video, I'm going to focus on this polymerization. I'm going to be talking about addition polymerization versus condensation polymerization. So let's get this out of the way, some words. We've already talked about how bromine, if you shake bromine, orange bromine water, if you shake bromine water and it loses its colour, becomes decolorized, then that compound that you shook it with is unsaturated. So unsaturated, what does that mean? Well, unsaturated means within the structure, within the molecular structure, you've got carbon, double bond carbon bonds present. Now, it's a bit of a mouthful. Carbon, double bond, carbon bonds present. We're talking about these things. Carbon, double bond carbon bonds present. Having those bonds present makes it like an alkene type molecule, and they react with bromine water. They decolorize it. So if we shake with bromine water and we look to see if it decolorizes bromine water, if the bromine water is decolorized, then the compound is unsaturated. If you shake it up with bromine water and it doesn't change the colour of bromine water at all, then it can't have a double bond, can it? It's the double bonds that do the reaction. If there's no double bonds, then there's no reaction. And we call those compounds that have all bonds being single bonds, we call them saturated. So organic molecules containing all single bonds, we say they are saturated. And there's another word you've probably come across when you're having your breakfast and you're putting margarine on your toast. You probably, if you read the margarine, it'll say rich in polyunsaturated molecules. So polyunsaturated molecules are molecules that contain lots of carbon double bond carbon bonds present. So the carbon double bond carbon bonds present, fundamentally, those things make alkenes, and we've talked about that homologous series, but with those present, they will react with bromine water. If there's none of those present, then the bromine water won't react, and therefore we can use it as a test. Test, the proof, the chemical proof for something in chemistry we call a test. So the test for unsaturation is shake with bromine water. Right, let's get on to the polymerization that I want to get onto. I'm going to be talking about addition polymerization. I've already talked about addition polymerization. If I take you back to that alkenes being polymerized, that was addition polymerization. And I can show you, I've actually bought the things I need to show you that today. And one of the hardest things on my syllabus is for my students to understand the difference between addition polymerization, which is what we've talked about, and condensation polymerization. Condensation polymerization is different to addition polymerization. Children find it really hard, and I'm hoping to explain it. I'm hoping that by the end of the video you'll know what the difference is. So let's start with a little demonstration to you. Here I've got paper clips. Now, if I represent these paper clip molecules, if each of these represents a molecule, if that's a molecule and it's one molecule, I want you to call single molecules that we're going to link together and make really long chains. The individual single molecules, I want you to call them monomers. Single molecules are known as monomers. So, I know it's not a monomer, it's a paper clip, right? But in your mind's eye, think of that as a monomer. And how many monomers do we have? Well, look, I've got lots of monomers here. I've got lots of monomers in this beaker of paper clips. And the idea of addition polymerization is that the monomers, just one monomer, another monomer, linked together. Often you need a catalyst. There, that's two monomers together. We call that a dimer. And three together, let's get a third one, clip it together. Now, believe it or not, that's called a trimer. And what about many together? Many together we would call a poly for many, polymer. Look, I built up a chain of that, but I could go on and on and on. Now, that's the idea of addition polymerization. Addition polymerization is the molecules just linking together over and over again, and thousands of molecules linking together make one polymer molecule, which is really long. And many polymer molecules are the basis of the plastics industry. So, polymers are the plastics of our world. Alkenes, they're the things with carbon double bond, carbon bonds present. Alkenes can be made to join up with each other, and when alkenes make polymers, we call them addition reactions, and therefore the polymer is called addition polymerization. And I can show you that happening. Let's get this underway so you can see. I have bought from the shops this morning, I bought a car repair kit. If you're like me, got cars that may have holes in them, then you buy a kit like this to sort out the holes. And what you do is you put glass fibre mat, that's a glass fibre mat, over the hole. And you make canoes like this as well. Glass fibre mats are used to make canoes, and you paint them with resin mixed with hardener. Now, it's these two things I want to talk about. This is styrene, and I'm going to put styrene in here. Let me just put it down here. So, this is styrene. I'm going to put some styrene into this cup. You see? Styrene is an alkene. These are alkene molecules. Now I can draw styrene for you. I think I've got a slide where it's included later. And what you need to make those monomers, many styrene molecules joined together, is you need a catalyst. This hardener is the catalyst. Now, let's take that off there. Let me just pour some hardener in here. Squeeze it in. That's a catalyst. So this will start the individual monomers, it will start them reacting together, and when they react together, hopefully they'll make a polymer. So this is like very similar consistency to what I started with. So in there, styrene, this is styrene, and it feels just like styrene. The difference is it's a bit red now because the hardener was red. Having mixed it up, I can then leave it to set, and I'm hoping in the time that I talk to you through the video it will set. I like to do this in a little sample bottle because I can break open the sample bottle when it sets and show you the lump of plastic that we get from it. So I'm going to leave these two, I'm going to leave them there, and I want you to picture in your mind's eye that there, the polymerization, the monomers are linking together, the catalyst is helping them to link together, the catalyst is causing the monomers to link together, a bit like paper clips linking together. And when they link together, thousands of them make really long molecules. When thousands have made really long molecules, then that will be a plastic. That plastic, believe it or not, will be called polystyrene. And polystyrene is what we're trying to make. And polystyrene is the basis of many glues. And if you were to put this over a hole on your car and then paint it with this, that's the idea of this repair kit, that the repair kit will, as a consequence of the reaction, this will stay in place, glued down when this sets. It will be glued down by the set. Once it's set, it'll be glued down by the polystyrene. Right, okay. So we'll come back to that, and I think we'll come back to it this lesson. So there's a few other things that I'm going to show you, which are going to take some time, and we'll come back and see if that's set. I'm hoping it will be set, but there's no guarantee. Those little things that are set up, they don't seem to be getting hot. Normally when they're getting hot, then I know the polymerization reaction is working, but let's move on and we'll come back to them. Now, in these addition reactions, in this kind of idea of addition reactions, I want you to think of individual molecules, like ethene molecules, many ethene molecules. We can show as N, and in brackets we've got ethene. Many ethene molecules will polymerize via addition polymerization. That polymerization is of an addition polymerization variety, and addition polymerization makes these kind of molecules polythene molecules, and they're used for shopping bags. So whenever we've got double bonds present like this, then we always get addition polymerization. I know I keep saying addition polymerization. I know I keep saying addition polymerization, but really that's what the video is about: addition versus condensation. So I'm hammering home the addition idea, and then I'll move on to the condensation idea. Now look, some very common addition, reaction mechanisms that make polymers. Now that's polythene that we've just been talking about. Polythene for shopping bags. If instead of starting with ethene, say you had a chlorine instead of a hydrogen, that would be called chloroethene, then the polymer would be called polychloroethene, and the common name for polychloroethene, the common name is PVC, polyvinyl chloride. Vinyl chloride is the old name that I grew up with. The modern name is chloroethene. But we still call it PVC, and you may have heard of UPVC window frames. They're made from this plastic that is made from chloroethene. And can you see double bond there means this is what kind of polymerization? Addition polymerization. Next, I tried to find some other examples. Perhaps it's not so clear, this one, but that was PVC windows. If you've got 3 carbons in a chain and an alkene like propene, propene makes polypropene, which is used for making modern day carpets and plastic crates. And this is what I've just been doing. Polystyrene is this, it's called a benzene molecule here. Don't need to know about it for GCSE, but if you've got a benzene molecule, 6 carbons, 5 hydrogens there, then the same thing will happen as I've explained with ethene, except it's not ethene, that's called styrene, and that polymer that it forms will be polystyrene, and that's the demonstration that I'm hoping to show you where the beakers are still pretty cold. Right, I might put more hardener in while I'm here, otherwise it will have to extend to another video. So let's go down and put more hardener in. That's more catalyst. So more catalyst has gone in. Just going to stir it up, hoping that it will speed up the reaction, and if the reaction gets speeded up enough, hopefully we'll get solid this lesson. If I leave that in there, it may be able to, if it solidifies, pull out the whole lump. So we'll come back to that. So that is addition polymerization. So what's the difference with condensation polymerization? Well, condensation polymerization, I wish they'd take this out of the syllabus. Unfortunately, it's not out yet. So, condensation polymerization happens when you've got 2 different molecules reacting. So I've got a molecule here. This is soon the next homologous series you'll see after alcohols is what we call a carboxylic acid. And anything with COOH is a carboxylic acid. And this has got a carboxylic acid group this side and a carboxylic acid group that side. It's what we call a dicarboxylic acid. And this one here, this molecule here, is an alcohol and an alcohol. That's the next homologous series I'm going to deal with, alcohols. And this is what we call a diol. So dicarboxylic acid with a diol, they react together. They make esters, and the type of ester they make over and over again, we call it a polyester. So this is an ester group, and this is the remains of that molecule here. That is the remains of that molecule there, and you make this ester linkage and you form some water. Now, when one of these joins one of those, you get one molecule of water. But what if you got loads? What if you got loads of those dicarboxylic acids and you've got loads of those dialcohols, then if you've got loads reacting, how much water are you going to get? You're going to get loads of water. And that's crucial, because the definition of condensation, polymerization is where molecules, monomers, link together, but they link and they eject small molecules like water. And when they eject the small molecules, that's what makes it condensation. So adding followed by ejecting, that whole terminology we use for that process is condensation reactions. So condensation reactions, all of them involve two molecules reacting, kicking out a small molecule. They kick out a small molecule because that's the reaction. What makes this end react with this end is that they make something else. They react and make a small molecule. That small molecule is kicked out. See, my classes find that hard to get their mind around. So I'm just going to stick with this. I've got a demonstration to show you in a minute. But look, one very famous use of this is proteins. Now, everyone knows proteins are made from amino acids. Well, amino acids need to link together. How many amino acids link to make a protein? Many, 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 many amino acids. So the amino acids, like that one and that one, two amino acids, they are like the monomers in these polymerization reactions I've been talking about. And what happens with the monomers is they link together, they kick out water. Each time one amino acid, another amino acid link together, they kick out water, and this link, called a peptide link, links them together. Now, look at the ends. That end can react with another amino acid. The COOH can react with an amine group, and so that amino acid group can react with a third amino acid. And what about this side? Well, that's an amine group. Here, amine. That amine group can react with another amino acid. It can react with the carboxylic acid side of the amino acid. Amino acids all have a carboxylic acid group one side and an amine group the other side. So any amino acid will come along, react there, and make 3 amino acids. And another one here make 4 and 5 and 6. And the chain grows and grows and grows and grows, and we get long chains. Those long chains we call polypeptides. Because of the peptide link, we call them polypeptides. And having got polypeptides, then when they grow beyond, the polypeptides fold over and hydrogen bonding takes place, etc. And then that final thing we call a protein. But it all starts with polymerization reactions. And what type? Condensation polymerization. This is not simple addition. This is addition followed by losing a small molecule like water, and therefore it's condensation polymerization. What I want to show you is just a very simple representation. These are like amino acids, different colors. I want you to consider those as monomers, and the monomers link together. That's polymerization. That arrow is polymerization. Link together and make really long chains. They're called polypeptides, and the polypeptides then will fold over, etc., and make the proteins of our world. And these processes in living systems are really vital and important, etc. So, the demonstration I'm going to do is to make nylon for you. Now, nylon, I need 2 chemicals. I need a dicarboxylic acid. See, look, COOH, that end, COOH, this end. I hope you're getting to grips with what the theme is. For condensation, we want both sides of a molecule to be able to react. So that's why it's got to be a dicarboxylic acid. And also, I want a diamine, because I want both sides to be able to react. And what happens is one side, one amine group, comes and reacts with a carboxylic acid group, just like amino acids did. And they kick out water, and that links that one to that one. But then the ends can carry on and react further, because they are diamines with dicarboxylic acid. They can react further, and the chain will then grow and grow and grow and grow. And because that link is called a peptide link, then I'm about to make nylon so you can see it. Because there's a peptide link, then those peptide links, nylon is a type of polypeptide. It's the links that define the poly when it comes to condensation and polymerization. Now, polypeptides like nylon, polyesters like Styrene that you might use to make cheap suits out of. My suits are made of Styrene, which is a polyester. Proteins, all of these things, all of these things are plastics. We make clothes out of plastic. This shirt, 60% polyester. My tie, I think it's 100% polyester. It's made with these kind of reactions. They are plastics. If I just, without burning it, if I just warm this up, it'll melt. I have a couple of fleeces that I've melted over the years because they've been heated up and they melt, and I have to chuck them away. So the real life applications for these, just to come back to this, that is getting really hot. So that I know is reacting, and you can see that the thing has solidified. I'm just going to let it carry on a bit. Even this second tube, that's warm, because that's got less catalyst in. That's got more catalyst in. We'll have a look at those later. But let's show you. Making nylon. Now, I make nylon using this apparatus here. One minute. Let's get you looking. This apparatus here. Oh, can you see this piece of nylon from the previous lesson? So, this is a roller. I hope you can see. Roller. If I start making nylon, I can draw out like a long thread by doing that. But I need two chemicals. Two chemicals that react together to make nylon. So what are the two chemicals? Well, I've got them here, believe it or not. One is a diamine, that's a molecule, 6 carbons, that's a hexadiamine, 6 carbons with an amine group. Believe it or not, it would be called 1,6-diaminohexane. 1,6-diaminohexane. Now, I do this in a tiny 5 ml beaker. Tiny 5 ml beaker. I just think it looks a bit more impressive when we use a tiny 5 ml beaker. But we need the second chemical. Now, the second chemical is a dicarboxylic acid. And here I'm going to float the dicarboxylic acid on top of the layer that I put in there, which is the diamine. So, dicarboxylic acid, diamine, in a small beaker. Can you see? There are 2 layers. There are 2 layers. A bottom layer and a top layer. And the reaction will happen at those layers. Now, I've got some tweezers here. I can hopefully pull out where the reaction happens. That is nylon. Now, if I put that on here, and then, oh, sorry, I was turning it the wrong way. So, back in with my tweezers, pull out some nylon that's being made. Pull out some nylon. Actually, let me just pull it back. If I do it carefully enough, I don't know if you can see, but once I get this going, I'm hoping then we can, I'm turning it now, hopefully the right way, and we get new nylon being made. Can you see that? Maybe you can see it there. That's better. There. Can you see? I'm turning it. I'm turning the handle. I'm getting more and more and more nylon being made. Because the interface, where one chemical joins another chemical, at that junction, we're having these peptide bonds being made. And what nylon is it's a polypeptide. It's linked together, lots of molecules being linked together via peptide links. And can you see, I'm turning this and I'm getting more and more and more. And I will get more and more and more nylon until one of the layers runs out. Now, rather than just keep doing this until a layer runs out. Now, you've seen me do this like 10, 15 times I've gone round and I'm still making nylon. That's good. But what if I stir it all up? Well, stir it all up, I'll just get a kind of mess of nylon. Shall we do that? So, I've got, let's just break it off here. Just show you there. That is the two layers. I'm hoping you see the two layers. Now I've got my tweezers. I can just stir it all up. And as I stir it up, can you see? That is like nylon being made on my tweezers. And the extra chemicals will just be left over in the small beaker. What I like to show is that from a small beaker, we can make quite a lot of nylon thread from a small amount of chemical. And that's it really. That's the demonstration of condensation polymerization. Nylon is an example of condensation polymerization. Watch. I have a picture of nylon. There, can you see this layer here is dissolved in water, and that contains the diamine. The diamine is at the bottom. The dicarboxylic acid, which is dissolved in hexane, is the top layer, and the two where they meet, when you're pulling it out, where they meet, the new nylon is being made at the junction, and pulling it out allows fresh chemicals to interface and react. And when they do, they react and they make this polymer. And remember, what makes a condensation is, as they do so, there is a small molecule kicked out every time. And so maybe there's water that is being made, and the water will mix with the water that's in the bottom layer. That is condensation polymerization. So to recap, addition polymerization, is where we've got an alkene and we just need like a catalyst. Now here, there we go. That is polystyrene. That is tough. Polystyrene in there. I could, in a class, I normally just do that and I break it open and I pass it around the class. But you can see there, probably if I whack it with a, that is pretty tough. And that lollipop stick will be really stuck in there. These things are great glues. I may have mentioned that a lot of the glues that are two-part glues use this idea of having something that's an alkene like styrene and putting a hardener with it to turn it into polystyrene. And the hardener allows you a certain amount of time to work with the glue and put it in position before it sets and holds the thing that you want it to hold. So there we've got a great example of addition polymerization. And this here, small beaker, that's a great example of condensation polymerization. And the difference is simply condensation needs two different chemicals reacting together and they kick out small molecules, whereas alkenes that are reacting, alkenes will polymerize by adding together, and you only need one chemical, an alkene. You might need a catalyst or you might need heat or pressure, but only one chemical. One chemical for addition, two chemicals for condensation, polymerization. And they're all plastics. All of these things I'm talking to you about are plastics. Nylon is a plastic. My tie, shirt, my suit, they're plastic fibre. I know it might not look a bit like that looks like a plastic. It might not look like that. But if you draw it out like you saw me do nylon, draw it out into a fibre, then those synthetic fibres are used in our world to make clothes. And they make the cheaper clothes. The clothes that I buy, the cheaper clothes. That's it, I think. I think I've finished the slide there. So we'll stop there and I'll catch up with you next time.